So, your first quiz. How many dimensions are required to describe each of these pictures? Two? Three? 10? Okay, so I will help narrow it down. 3 of the pictures, actually, sorry, 2 of the pictures require one answer, and then one, all right. These 2 require one answer, the other 2 require independent answers.
Is the little dot, that's one dimension, the 2 picture in the middle?
This is 0 dimensions.
Oh.
It's a point.
But a point where?
It doesn't matter, right? If I have an entire universe described as a point, any answer is within it.
Nothing matters and
Right.
everything's right.
Exactly.
At the same time.
This one though, 1 dimension. And these both, because I can display them here, require 2. They probably are mappings. They're probably projections from somewhere else. So this is probably what you're used to seeing. Right? So this is your basic Euclidean drawing of the same data. Right? So everybody had geometry in high school. We got to do all these drawings. But what's the most dimensions in which these drawings can exist?
So your computer melts?
Hmm?
So your computer melts?
That's a good answer. How about a mathematical form of that answer? Infinite. So any of these can exist in any number of dimensions. Right? So this lowly point that itself is described by 0 dimensions can exist, to your point earlier, of where. It can exist in a higher dimension space. So in this case, I've drawn it in 3 space. Right? I've also drawn this in 3 space, and because it's curved here, right, it probably is represented in more dimensions as something flat. Okay. So with enough dimensions, everything's linear. So hyperplanes, right, will cross any number of dimensions. So a hyperplane is just one less than the total number of dimensions you have. We're used to thinking in terms of basic geometry because we see 2 dimensions and we see this table as a plane. Well, it just is 2 dimensions in our 3 space. The same thing applies, right? 3 dimensions, what we live in, is actually a plane in 4 space. Linear has a lot of useful mathematical properties that get used by machine learning. So that's why we actually care about any of this. That's about all we're really going to say about linear algebra, mostly because really covering it would take several hours. Hopefully that gets kind of your brains working back to, oh yeah, all that hard stuff where I was trying to map, all these 2 and 3 dimensional concepts onto 4, 5, and infinite dimension spaces. Right? So in machine learning, we frequently talk about 1,000 and 10,000 dimensional spaces. Right? So that is a common thing in machine learning. So, now we have some basic statistics. More fun stuff. So variance. Variance is going to be critical to basically machine learning, but also what you do, right? So everybody here presumably is some kind of technical trader. So variance is important to what you do. So, it is based on some basic concepts. Right? Your real-world observations cannot represent, right, the entire set of possibilities. Right? I am only perceiving, right, what has happened to the stock in the past, right? Or whatever the instrument is that I'm monitoring. Right? I'm seeing it real time, I'm seeing it as it goes, and I can look backward. I cannot look forward. So by definition, it is impossible to look at the entire set. Because I, as a human, am bound by time. It's annoying. So, since we don't actually get to see everything, that means we're always estimating the mean and the variance, right? Because variance itself is defined as difference from the mean for an entire population. So we have to have a mean. So we can only see the mean for the observations we've seen. Right. By the way, stop me if I ever go too fast. I've tried to make this very digestible in the quick time we have allowed. And then variance is going to be a measure against that mean for the observations that I've seen so far. So I can estimate that into the future. So generally speaking, what we do is we take our observations, we make them comply with an estimate, and then we project the estimate into the future. So the important thing about our estimator function, right, it looks at our n observations, but without observational bias. That's critical, because it basically doesn't exist. Right? Who actually has observed the stock market without bias? And I don't mean your personal bias, but I mean actually the observations themselves. Right? How are the observations over the last couple of months biased? Bullish. Okay.
Well, I mean, you're basically looking at more than one data point at moving timestamp, so you're always looking at trends.
You're always looking at trends, right? So you're looking at, that trend is actually called a Markov model, right? So you're actually looking at hidden Markov models. There are ways to represent some of those things. There are actually algorithms for determining the hidden Markov model. But nonetheless, if I only use, say, a few months of data or a few years of data, right? I could be looking at a bullish. I can be looking at trends like Brexit. I can be looking at trends like quantitative easing, right? Much longer trend, right? We always talk about the idea that the stock market is fractal. Well, that means if there is any long-term trend, it is absolutely biasing all of our short-term observations. So we want the law of large numbers, but we're always influenced by something at a higher level of our fractalness. Right? So the only way we can even come close is if we actually look at n instead of number of data points, we look at it as number of situations. There's not a lot of literature on that. Right? Our models, I think there's real research there for what that means. Okay. But, intuitively, 2000 bubble, 08 bubble, the 10 flash crash, the 13 crash, the various bullish bubbles, right? The 05 bubble, the now bubble, when is it going to end? All of those things are different scenarios, and they're basically each one n equals 1. So just because we look at 10 years of data doesn't necessarily mean we're looking at hundreds of thousands of data points. Right? Unless the market has zero correlation to other instruments, which we all know instruments move together. And we'll talk a little bit about correlation and how to describe that mathematically, but it turns out that the stock market moves together quite a lot. Especially instruments like iTrade, like the S&P 500, right, which is essentially just large caps. So, we'll start getting into some basic math. Here's your population mean. So our mean is 1 over n times the sum of all of our observations. So, slightly annoying mathematical description, but pretty easy to implement for those of us who are computer programmers. Just write a for loop, add them up, divide by the number of observations. I know just from a survey in the past, a lot of people here have at least some level of programming background. This is probably a good time to talk about what our backgrounds are. So who here has, say, moderate programming experience or better? Okay, light programming experience or better? And no programming experience. Okay. Of the people who have no programming experience, who does not have a significant math background? Okay, good. Everybody either has significant math, which will work for the slides, or significant computer background, which will work for pretty much my alternative explanations. Okay, so there's our population mean. That's pretty simple. So this is what our population variance looks like. Basically, we take the difference of each observation against the population average, population mean. We take that difference, we square it, we sum all those squares, and then we divide by n. So it's the square of the standard deviation, because standard deviation is by definition the square root of the variance. So that all simplifies down to there. You can take your pick as to whatever's easiest to implement. These are all equivalent.
For some people that are not programmers, you can do it in Excel.
Mhm.
Pull it out.
We have a cheat sheet later with the Excel functions. I can't remember how many slides ahead it is. It's probably 6 slides ahead. We'll have a cheat sheet for how to do all of these basic calculations in Excel. Unfortunately, it doesn't work it doesn't have the exact formulas in OpenOffice, but they're pretty easy to translate. Okay, so our sample mean, that looks very similar. So the only difference here is that we were talking about little n instead of big N. So big N is the total number of objects in the population. Since we're time bound, we can't know the ones from the future. So we can't know this one. We can only know this one. And that'll become important for a couple definitions later. Slightly important. Otherwise, the means are the same. Biased sample variance, it's not quite the same. So the biased sample variance is defined by what we have seen. So we take a sample with replacement. This becomes important not only to this statistical concept, but to other statistical concepts that are in machine learning. So when we take a sample from an observation set with replacement, that means that we don't actually remove it from the set. So if I have 2 apples and an orange, and I observe an apple, I still have 2 apples and an orange in my population. And if I observe randomly, I still have a 2/3 chance to observe an apple. Right? That's with replacement. Without replacement means when I observe the apple, I remove it. Very few things are done without replacement. And specifically, most of the machine learning algorithms do things with replacement. And it will seem unintuitive to you. And it will annoy you for a while. And that's okay. You still do it anyway. It's mathematically sound. So, when we observe with replacement, we go for I less than j. So j is our current marker in time, I is everything we've seen up to then. And we look at the differences. We square them, and we divide by n squared. This is a quadratic algorithm. It's slow. There's also faster ways and better ways. But this is what a biased sample variance looks like. Unbiased gets modified. So here, we actually pre-calculate the sample mean. So we make one loop through, right? We calculate the sample mean, and then we observe everything that we've seen in our sample. So like everything from the beginning of time to today. And we calculate the difference between that and the mean, square it, and then instead of dividing by n, we divide by n minus 1. Right? That has to do with these factors and then simplification of the formula. Saw some quizzical looks. Are there any questions, or are we willing to accept that as on faith? Okay, we accept the mathematicians on faith. Good, because I had to myself. Because even though, so I've read through the books again for these series of presentations, and I have a degree in computer science. And the year before I enrolled, my catalog would have also given me a double major in math. And I still was like, oh yeah, what is all that crap? But it all works. Okay, so this is the basic statistics that we need. So then we start talking about the distribution of the sample variance. So since the variance itself, right, is a function of random variables, we can look at the variance and study its distribution. So that means that the bound on our variance, it can only be so wrong. And that's where we start, that's where we'll actually be able to learn interesting observations about things we will not be able to see in the future. Because we have mathematical proof that variance given a number of observations. Now, what's the key about those observations? They're bound? Biased. Right. They have to be unbiased. Right? So to the extent that they're biased, this does not hold. And quantifying that, I have not found good literature on. If anybody actually uncovers that, I would love to see good literature on correlation percentages and how they chip away at the validity, at the confidence interval of our variance. Usually in all the literature I've found, things are either assumed biased or unbiased. And almost everything in machine learning assumes unbiased. So, but given things are unbiased, Samuelson's inequality tells us that our mean will be within, let's see, that one is variance times n minus 1 square root. Okay, so if we increase n, this relatively quickly becomes small. So that means with a few hundred observations, if they're unbiased, I can reach a relatively small chance that the average I've observed will differ from the actual real observation, or the real mean.
That's not the formula you're looking at.
Say again?
I mean, that's not what the formula says, right? That one says that how far away an individual point is going to be maximum from.
Yes. So this one is plus or minus. So that's.
And it's going to be bigger the more samples you go.
No, it's going to be within this bound. So it's going to be greater than the minus and less than the plus.
I think his point might have been that as n increases, your bounds also increase, but at a square root rate. Was that your point?
Yeah, I mean, also with the statement of that inequality above, if you read it, that's what it says. It's something else. But I know what you mean, but it's just the wrong slide of that.
So this doesn't necessarily increase.
Samuelson's whatever inequality states bounds on the values that individual observation and sample can take, given that sample mean and variance have been captured. So if you have a sample mean and the variance, the individual points are going to be maximum sigma times square root. But the point is, the more points you measure, the further the individual can be away.
Not true.
It's actually true, because if you have a large amount of points, the variance is less determined by the individual. So one individual can be much further away. If you have fewer points, then a single individual is going to determine the variance a lot more.
Yeah, but
So
It can be true. It's not necessarily true.
Not necessarily. If your data points are close there, it can be
It's a
very small
straight
variance.
line.
It has no relevance to it.
The average.
We're not getting it. We gotta listen. So if you have a mean and you have a bunch of points that are distributed around that, right? If you have only, let's say, 3 points.
So one distribution could be that two of them are very
Can I-
close and one is far away.
Right.
Yes.
In that case, because you have only 3 points, an individual can only be so far away. Because if it was further away, the variance would be much larger. However, if you have a lot of points, then one individual is not going to dominate the standard deviation very much. So that individual can be a lot further away.
But that-
and that's what that inequality says. But I do agree that the more points you have, the closer the standard deviation of the mean is. But that's a different problem.
Kevin, just quickly. If any of you not registered your car, like if you're in a parking lot, please do. I think that's the announcement about that they'll probably give you a ticket or something. If you're parked in a parking lot, you just need to just tell them the car number.
Yeah, basically you
To
just.
the left of the desk.
Yeah, just to the left of the registration desk.
Sorry. Clear the room.
Newbies!
It's a biased sample.
Yes.
Yeah, the rookies now.